Hello everyone. In today's lecture we will continue working on the time domain representation of Lti systems. In the previous couple of lectures we've learned about discrete time Lti systems, and we have defined the so-called impulse response of a discrete time Lti system, which is h of n, which is simply the output of the Lti system if the input is an impulse delta of n. And we have proved mathematically that the output from an Lti system is a convolution between the input and the impulse response. And we've applied this to many problems, and we have seen the procedure which we can use to evaluate the convolution for discrete time systems, which we have called the convolution sum. In today's lecture we will do the same thing but for continuous time systems. So if we have a continuous time Lti system, we can also define the so-called impulse response, but now it will be called h of t, where h of t is the output coming out from the system if the input is an impulse delta of t. So if we have a system with input x of t and an output y of t, the impulse response delta of t is defined as follows. If we let the input x of t to be an impulse at instance 0 delta of t, in this case the output coming out from the system will be the impulse response h of t. It's the same definition we did for discrete time systems. And similarly, it could be shown mathematically that the output from a continuous time Lti system, y of t, is equal to the convolution between the input and the impulse response, x of t convolution with h of t. Of course, in the discrete time system, the definition of the convolution was basically summation of x of k times h of n minus k and so on, because the variable was discrete n. But here the convolution is called the convolution integral, and it is defined slightly different than the convolution sum. So going back to our slides over here, the output y of t of a continuous Lti system is given by the convolution integral of the input x of t and the impulse response h of t. And the convolution integral is defined as follows. So y of t is equal to x of t convolution h of t. First step, we replace the variable t with a dummy variable tau. So in order to evaluate the convolution integral, we start with x of t and h of t. First step is to replace t by tau, so x of tau and h of tau. Then we will choose one signal to keep as is. Let's say we'll keep x of tau as is. So h of tau first will become h of minus tau, which is mirroring the signal, and then shifting to be h of t minus tau. And now we can multiply x of tau times h of t minus tau under the integration right now. So the first definition, or the first form of the convolution integral, is multiplication of x of tau h of t minus tau d tau. So integration x of tau h of t minus tau d tau. The second form is simply to keep h of tau as is and mirroring x of minus of tau to be x of minus tau, and then shifting to be x of t minus tau, and then multiplying h of tau with x of t minus tau under the integration. So integration h of tau x of t minus tau d tau. And this is the second form of the convolution integral. Integration h of tau x of t minus tau d tau. It's very similar to the convolution sum, except that here you have a continuous variable. That's why we have an integration rather than a summation. And note that the variable is tau right now. In this integration, it's integration with respect to the variable tau, where for this integration t is a constant inside the integration. Okay, and for the first step is to replace t with tau. X of t becomes x of tau, and h of t becomes h of tau, and then h of minus tau, and then h of t minus tau, then multiply these two together. Or you can do it the other way around. And similarly, if t is negative, we will shift h of minus tau to the left. If t is positive, we will shift h of minus t to the right. And we can choose the other way around to keep h of tau as is and mirroring and shifting x of t. Okay, so let's start with our first example over here. We have an LTI system whose impulse response is defined as u of t minus u of t minus 2, which is a rectangular pulse starting at time instant 0, ending at time instant 2. And we need to find the output for the input x of t defined as u of t minus 1 minus u of t minus 3. So let me start by plotting h of tau and x of tau and moving on. So going to our whiteboard over here, let this be h of tau, the impulse response, which is u of t minus u of t minus 2, as you can see over here. U of t minus u of t minus 2. So it's basically a rectangular pulse starting at 0 up to 2. And over here, let's plot x of tau, which is a rectangular pulse starting from 1 up to 3. So it's u of t minus 1 minus u of t minus 3. So it's a rectangular pulse from 1 up to 3. And of course the height is 1, the height is 1. So let me first choose one signal to keep as is and the other signal to mirror and shift. I will keep x of tau as is, so I will start mirroring and shifting h of tau. So first step is to mirror. We'll make it h of minus tau, like this. So it should be from minus 2 up to 0. And next we will shift the signal to be h of t minus tau. And in this case, this 0 will become t, and this minus 2 will become t minus 2, and the height is 1. And now we can start change the value of t and see the overlap between x of tau and h of t minus tau and do the integration. So first step, we can clearly see that if t is less than 1, then there will be no overlap, and x of tau times h of t minus tau will give us 0. So moving on, I can write that y of t will be equal to 0 when t is less than 1. So if t is less than 1, there will be no overlap and y of t will be 0. But if t is larger than 1 and less than 3, so if t is larger than 1 and less than 3, the situation would be like this. The rectangular pulse we have over here will be shifted in this way. This will be the new value of t. This would be the new value of t minus 2. And now there will be some sort of overlap between tau equal to 1 up to tau equal to t. So the integration in this case will be from 1 up to t. And we're multiplying x of tau with h of t minus tau, which is 1 times 1. So I can write integration from 1 up to t of 1 times d tau. Please note that this pulse has a width of 2, and this pulse is also having a width of 2. So the condition t larger than 1 and less than 3 is equivalent to having t minus 2 less than 1. So the next condition would be if t is larger than 3 and t minus 2 less than 3. In this case, the shifted pulse would be like this. So this edge is t is larger than 3, and this edge is t minus 2 less than 3, which is t less than 5. So the third interval would be t larger than 3 and less than 5. And in this case, the integration will go from t minus 2 up to 3. So the integration will go from t minus 2 up to 3 d tau. And the last interval would be if t minus 2 is larger than 3, which is t larger than 5, there will be no overlap and the result will also be 0. So this will be happening if t is larger than 5. So let me go back over here and maybe I can just keep it like this. It will be 0 if t less than 1, and also it will be 0 if t is larger than 5. So let's do the integration in this case. So y of t is equal to 0 if t is less than 1, and for the interval t larger than 1 and less than 3, we are integrating d tau, which will give us tau, and then we'll substitute with the limit, so it will be t minus 1. So we'll be having t minus 1, which is a straight line with a positive slope. And the next interval would be from t larger than 3 and less than 5. And in this case, from 3 to 5, integrating d tau will give us tau. Substituting with the limit will be 3 minus t plus 2. So 3 minus t plus 2 would be 5 minus t. So we'll be having 5 minus t, which is a straight line with a slope of negative 1. And if t is larger than 5, we'll be getting a 0. Let's try to plot this and see how it goes. So now, this is the time, and now we're plotting y of t, the output signal. So the output signal is defined over 4 intervals. When it's less than 1, it's 0. When it's larger than 5, it's 0. So 2, 3, 4, 5. Before 1 it's 0, after 5 it's 0. From 1 to 3 it's defined as a straight line t minus 1. So t minus 1 at 1 will be 0, and t minus 1 at 3 will be 2. So this is 2. And for the interval from 3 to 5, we'll be having 5 minus t. So at instance 3, 5 minus 3 is 2, and at 5 it will be 0. So it's kind of a triangle. So the convolution of 2 rectangular pulses will give us a triangle. Okay, let's go back to our slides over here and see the slides. So we'll do the convolution, and here in the slides I've chosen to keep h of tau as is and mirror and shift x of t minus tau. That's why you might note a different limits of integration, because in the whiteboard I've chosen to keep x of tau as is and mirror h of tau, but the final result is the same. And this is a very good example actually, because you can follow the steps in the slides and the ones in the whiteboard and see that even though we have chosen to mirror and shift the different signal, but we're still getting the same final result. So it's 0 for t less than 1, 0 for t larger than 5, t t minus 1 and 5 minus t, and this is doing it graphically. So keeping h of tau as is, x of tau, x of minus tau, x of t minus tau. This is a mistake over here. This should be x of t minus tau, and this would be the final result. Okay, let's consider our next example over here, where we have an RC circuit, the one we have seen maybe in circuits, and we are given the impulse response to be 1 over RC e to the negative t over RC u of t. And we need to find the output of such a circuit for an input x of t equal to u of t minus u of t minus 2. So again, this circuit is an LTI system, linear time invariant system. We have an impulse response, we have an input. So in order to find the output, we need to do the convolution. So first step, we'll do it by plotting h of tau and x of tau, and then choosing one signal to keep as is and the other one to mirror and shift. Let's try to plot h of tau. It's an exponential function times u of t. So it starts at 0 going up to positive infinity. So let's go to our whiteboard over here. And this is h of tau. It's simply an exponential function, decaying exponential function starting at instant 0 because it's multiplied by u of t. And the equation of h of tau is 1 over RC e to the negative tau over RC u of tau. This one. And x of t is a rectangular pulse starting at 0 ending at 2. So let me plot over here x of tau. And x of tau simply a rectangular pulse from 0 to 2 with the height of 1. And next we need to choose one signal to keep as is and the other one to mirror and shift. And here it seems easier to actually mirror and shift x of tau. It's a simpler function. Usually we choose a function that's easier or simpler to mirror and shift and do so. So first I will get x of minus tau. So it would be a rectangular pulse from minus 2 to 0. And then I will start shifting the signal. So this 0 becomes t, and this minus 2 becomes t minus 2, and this would be x of t minus tau. And now we'll start changing the value of t and observe the intersection and perform the integration. So if t is less than 0, which is basically a rectangular pulse like this one, there will be no overlap, and the pulse over here multiplied by 0, so we'll get 0. So I can write the following: y of t is equal to 0 if t is less than 0. But if t is larger than 0 and t minus 2 is less than 0, if t is larger than 0 and t minus 2 is less than 0, as the case here drawn in red, in this case the overlap will be from 0 up to t, and in this case the integration will go from 0 up to t. So let me write down the following. In this case we will be having an integration from 0 up to t. What is being integrated over here? We're integrating h of tau times x of t minus tau. X of t minus tau has a height of 1, and h of tau is 1 over RC to the negative tau over RC. So we're simply integrating 1 over RC e to the negative tau over RC d tau. And this would be true if t is larger than 0 and t minus 2 less than 0, which is basically t less than 2. So t less than 2. Now, what would happen if t minus 2 becomes larger than 0. If t minus 2 becomes larger than 0, we will be getting this situation. The rectangular pulse will be like this. And the overlap would be from t minus 2 up to t. And in this case, the integration will be from t minus 2 up to t. So, if t minus 2 is larger than 0, in other words, if t is larger than 2, the situation would be like this. If t is larger than 2, the integration would go from t minus 2 up to t. From t minus 2 up to t. And again, we are integrating h of tau, which is 1 over rc, to the negative tau over rc times 1. So we'll be integrating 1 over rc e to the negative tau over rc d tau. Next, we need to evaluate the integrations. So y of t would be equal to 0 if t is less than 0. And next, for t from 0 up to 2, we're having this integration. So 1 over rc will get out of the integration, and this kind of integration you have to divide by minus 1 over rc. So effectively we're multiplying with minus rc. So it will cancel out with this 1 over rc over here. And we will end up with e to the negative tau over rc with the limits. So we can write e to the negative tau over rc and have a negative sign over here. Let me do it in details. So I have 1 over rc as a constant, and since we are integrating with respect to tau, we have to divide by minus 1 over rc, which is multiplying by minus rc. So I will be multiplying this by minus rc, and then we will be having e to the negative tau over rc, and now we can put the limits, which is from 0 up to t. And of course, this will be true for t larger than 0 and less than 2. So t has to be larger than 0 and less than 2. And the next interval where t is larger than 2, it's the same integration but with different limits. So if t is larger than 2, I will put the same expression, which simply will be this rc will cancel out of this rc, and we'll be having minus e to the negative tau over rc, and the limits will be just different, will be from t minus 2 up to t. So it will be from t minus 2 up to t. So moving on, y of t is equal to 0 when t is less than 0, and when t is larger than 0 and less than 2, we will be having the following: e to the negative t over rc minus e to the power 0, which is 1, and this negative sign will just exchange the two terms. It will be 1 minus e to the negative t over rc. So 1 minus e to the negative t over rc. And for the last interval where t is larger than 2, and again this negative sign will just swap the two intervals over here, so we will be having e to the negative t minus 2 over rc minus e to the negative t over rc. So it will be like this: e to the negative t minus 2 over rc minus e to the negative t over rc. And of course over here we can take e to the negative t over rc as a common factor, and you will be getting the following expression: y of t equal to 0 when t is less than 0, and when t is larger than 0 and less than 2, we'll be having 1 minus e to the negative t over rc. And when t is larger than 2, you can take e to the negative t over rc as a common factor, and we'll end up with e to the power 2 over rc minus 1. So e to the negative t over rc times e to the power 2 over rc minus 1. Okay, so let's go back to our slides and see how does it go. So again, we'll do the convolution, and here I've chosen to keep h of tau as is and x of t minus tau, the signal to be mirrored and shifted, same as we did in the whiteboard. So it's going to be 0 for t less than 0, and then we're integrating from 0 up to t for the interval from 0 to 2, and then integration from t minus 2 up to t for the interval larger than 2. One thing over here, in the example we were told to put RC equal to 1 second. In the whiteboard I have solved using RC, we kept them, so it's going to be almost the same. Let's see how it goes. So do the integration. For t less than 0 we'll get 0. From 0 up to 2 we'll get 1 minus e to the negative t, and if t is larger than 2, e to the power 2 minus 1 times e to the negative t. In the whiteboard, we kept RC. If you put RC equal to 1, you will be having 1 minus e to the negative t, which is this expression. And if you put RC equal to 1, you get e to the negative t times e to the power 2 minus 1, which is e to the power 2 minus 1 times e to the negative t. So same expression, but we did it even in more general case on the whiteboard. Of course, if we try to, this is the graphical representation of the convolution integral, we'll keep h of tau as is, x of tau, x of minus tau, x of t minus tau, and this would be y of t. It will be a rising exponential from 0 up to 2, and from 2 up to infinity it will be a decaying exponential. And actually, this basically agrees with what we have learned in circuits, because you are applying a rectangular pulse from 0 up to 2, and the circuit over here is an RC circuit where the capacitor will start charging when this pulse is applied, and when the pulse stops, then the output will start decaying because the capacitor will be discharging. So over here it's a charging capacitor, and here we have a discharging capacitor. So what we are learning over here agrees with what we have seen in circuits. It's simply a different way of computing things. In circuits, we have learned about capacitors charging and discharging. We use KVL and KCL. Here, we use a different approach. If we know the impulse response and the input, we can get the output. And actually, the two approaches agree with each other. We get the same final result. And this is very good. And actually, it's kind of eye-opener. It's actually helping us to understand that all branches of science are achieving the same result. Next example, you have an impulse response h of t equal to u of t plus 1 minus 2 u of t minus 2, and the input is t minus 1 times u of t minus 1 minus u of t minus 3, and we need to find the output. So an LTI system, input, impulse response, so we do convolution. In order to do the convolution over here, we always do it graphically. Let's start by plotting h of t. So h of t is u of t plus 1 minus 2 u of t minus 2. And let me take some time to plot this carefully. So h of t is equal to u of t plus 1 minus 2 u of t minus 2. Let's move to our whiteboard over here, and this is h of t. If we try to plot this, and let's try to do it carefully, if this is a 0. So the first unit step over here is the unit step starting at minus 1 and going from 0 to 1, like this. And the second unit step over here is the one starting at 2, but it has a negative amplitude of -2. So now, if we add these two together, are we adding them or subtracting them? We're adding them if we have this -2, because we already took the negative sign along with the function over here. So we are as if we're adding these two curves together. So adding these two curves together, let me use a different color. So 0 plus 0 will be 0. 1 plus 0 is 1. And over here, starting at instant 2, we have 1 minus 2, which will give us -1. So the resulting function will be this function in orange. So let me go on and plot this one. So the impulse response over here h of tau, and let's move back. So it starts at -1, and at 1 it goes to -1. So at -1 over here starts going up to a value of 1, and at instant 2 it goes down to -1 up to infinity. This is h of tau. Okay. The input has the form x of t equal to t minus 1, which is a straight line, times u of t minus 1 minus u of t minus 3. So u of t minus 1 minus u of t minus 3, this part corresponds to sort of a rectangular pulse from 1 up to 3 and 0 otherwise. So this part over here corresponds to this rectangular pulse. Now let's try to plot this t minus 1 thing. It's a straight line. So at 0, at instant 0 it will be -1, and at instant 1 it will be 0, so it's a straight line going like this. So this line in red is t minus 1. Okay, and of course at instant 3 it's 3 minus 1, so it's equal to 2. So the value at this instant is 2. Okay, so multiplying these two together, the straight line t minus 1 times this rectangular pulse will give us what? So for this interval will give a 0, because it's 0, the rectangular pulse is 0, multiplied by a straight line, so it's 0. And for the interval for t larger than 3, it's another 0, because the rectangular pulse is 0. And the only part of the straight line which will not be multiplied by a 0 is this part. It's multiplied by a 1. So this is the only part of the straight line which will be kept, actually. So x of t, the input, is kind of a straight line starting at instant 1 at a value of 0 and ending up at instant 3 with a value of 2, and it will be 0 otherwise. So moving on, let me draw x of tau. So starting at 1, ending at 3, and straight line from 1 to 3 like this, and the maximum value over here is 2. And the equation for this straight line is t minus 1, but now since we have replaced t with tau, so it's tau minus 1. So let's go back. Now we have an LTI system with impulse response h of t, x of t. We have drawn x of tau, h of tau. Now we need to do the convolution. So let's go back to our whiteboard to carry on with the convolution. I will actually choose to keep h of tau as is and mirror and shift x of tau. So first, mirroring x of tau, it will be x of minus tau, and it will be starting from minus 1 up to minus 3, and the straight line will go like this, and the equation of the straight line would be minus tau minus 1. If you substitute for tau equal to minus 1, you will get a 0, and if you substitute for tau equal to minus 3, you will get 2. So now we have the correct equation, minus tau minus 1. We're simply replacing every tau with minus tau. And the next step would be actually to start shifting this signal. So now this minus 1 becomes t minus 1, and this minus 3 becomes t minus 3. And now for the confusing part, the equation for the straight line. If this is x of tau, it's tau minus 1. So x of t minus tau would be replacing every tau by t minus tau. So I will replace this tau by t minus tau. So it's t minus tau minus 1. This is the equation for the straight line. Substitute with tau equal to t minus 1, you will get a 0. Substitute with tau equal to t minus 3, and you will get 2. And now we will be changing the value of t and observe the interval of overlap and try to write down the equations. Let me draw it one more time because this waveform is kind of confusing. Let me draw it one more time over here. So now we have h of tau. This is h of tau. H of tau starting at minus 1. So here, minus 1. Have a value of 1 up to instant 2. And at 2 we go down to minus 1. And over here, let's draw x of t minus tau. So it starts at t minus 3 up to t minus 1. So let's start like this. This is t minus 3, and this is t minus 1. So the first interval would be if t minus 1 is less than minus 1. In this case, there will be no overlap and the convolution will be 0. So t minus 1 less than minus 1 simply means t less than 0, correct? If t minus 1 is less than minus 1, so t is less than 0. So the first interval would be like this, y of t equal to. It will be 0 if t less than 0. So what about the next interval? If you go back over here and let's try to see if t minus 1 is larger than minus 1. So let's try to plot it over here, and if t minus 1 is larger than 1, this would be the new t minus 1, and this edge over here would be the new t minus 3. So in this case, the overlap will be from minus 1 up to t minus 1. And in this case, we will be multiplying h of tau, which has a value of 1, with this straight line. And if you remember, the equation of this straight line was t minus tau minus 1. So the equation over here is t minus tau minus 1. So we'll be multiplying 1 times t minus tau minus 1, and we'll be doing the integration from this starting point minus 1 up to t minus 1. So it will go like this. So if t minus 1 is larger than minus 1, it simply means t larger than 0. So if t is larger than 0, there will be the integration would be from minus 1 up to t minus 1, and we'll be integrating 1 times t minus tau minus 1. So t minus tau minus 1 d tau. And this integration would be true as long as this edge, which is t minus 3, is less than minus 1. So t minus 3 less than minus 1, which is basically t less than 2. So this interval will start t larger than 0 and less than 2. What about the next interval? So let's go back over here and try to see the next interval. Now note that this triangle, the width of this triangle is 2, whereas the width of this part is 3. So we'll be having a situation where the triangle will be completely under this rectangular pulse. This would happen if t minus 1 less than 2, whereas this edge, which is t minus 3, larger than minus 1 and less than 2. So let's try to do it in detail. So t minus 1 less than 2, which is t less than 3. So the third interval will be t less than 3. And this edge, which is t minus 3, should be larger than minus 1. So t minus 3 larger than minus 1, it means t larger than 2. So for the interval t larger than 2 and less than 3, the integration will be from this edge, which is t minus 3 up to t minus 1. So we will be doing the integration from t minus 3 up to t minus 1. And the function under the integration is 1 times this straight line, which is t minus tau minus 1. So again, integrating t minus tau minus 1 d tau. And the next interval would be when t minus 1 is larger than 2. And let me draw it in a different color. The new interval would be like this, which is t minus 1 larger than 2, and this edge, which is t minus 3 less than 2. So if t minus 1 is larger than 2, it means t larger than 3. So going over here, I can write down that y of t is equal to, and the interval would be t larger than 3. Going back, so t minus 1 larger than 2, which is t larger than 3, and this edge, which is t minus 3 less than 2. So t minus 3 less than 2 means that t is less than 5. So the new interval would be from 3 to 5. And in this interval, the integration actually will be divided into two parts. The first part is from t minus 3 up to 2, and the second part will be from 2 up to t minus 1. So let's try to write it down. So the first integration from t minus 3 up to 2 integration from t minus 3 up to 2, and the function we are integrating is t minus tau minus 1 d tau, plus the next interval would be starting at 2 up to t minus 1. So integration from 2 up to t minus 1, and now the function inside the integration is the same straight line, t minus tau minus 1, but multiplied by minus 1 in this case. So it's gonna be minus t minus tau minus 1. Okay, and then the next interval would be when the triangle is completely in this part, in this region, where this edge, which is t minus 3 larger than 2 or t larger than 5. So the next interval would be y of t equal to when t is larger than 5. And in this case, if you go back, we will be integrating minus 1 times this straight line. So minus t minus tau minus 1. So we'll be integrating minus t minus tau minus 1 d tau. And the limits of the integration will be from this edge, which is t minus 3 up to t minus 1. So from t minus 3 up to t minus 1. So as you can see, this problem is quite complicated. We have 1, 2, 3, 4, 5 intervals, and now we need to evaluate these integrations. These integrations are kind of straightforward. Integrating t with respect to tau, t will be a constant, so we'll get a tau. Integrating tau, d tau is tau squared over 2, and now you can do substitution with these limits. So I will leave this part for you guys to do. So now we can go to the slides and see the final answer. So now we have this Lti system, and here in the slides I've chosen to keep x of tau as is and h of tau to be mirrored and shifted. But in the whiteboard I did the other way around. I kept h of tau as is and I mirrored and shifted x of tau. That's why the limits of the integration are slightly different and the function inside the integration is different, but the final result would be the same. So this would be the final result. I want you guys to evaluate the integrations we have seen on the whiteboard and compare them with these final results. And here I kept x of tau as is, mirrored h of tau, and then shifted h of tau. Now this would be a plot of the function y of t. Now, next example, an Lti system who has the impulse response as an impulse function. So the impulse response h of tau is now a, which is a constant, delta of t minus t naught, and t naught is a constant. And now we need to find the output y of t for any input signal x of t. So the impulse response over here, h of tau, is h of t is a delta of t minus t naught, and we need to find the output y of t. So we'll do the convolution, which is the integration from minus infinity up to infinity, x of tau h of t minus tau d tau. So in order to evaluate this would be the integration from minus infinity to positive infinity, x of tau, which we do not know, times h of t minus tau. So if h of t is a delta of t minus t node, h of t minus tau would be simply replacing every t with t minus tau. So it will be a delta of t minus tau minus t node. So a delta of t minus tau minus t node and integration with respect to tau. Now we are evaluating this integration with respect to tau, so tau is the variable. And as you remember in the previous chapter, integrating a function multiplied by an impulse will be equal to the function evaluated at the instant where the impulse happens. So now this impulse, considered as a function of tau because you are performing integration with respect to tau. So this impulse will happen at t minus tau minus t node equal to 0. In other words, at tau equals to t minus t node. This impulse is happening at tau equals to t minus t node. One might ask why we are evaluating or looking at this impulse as a function of tau, not as a function of t. Because the integration is with respect to tau, so tau is a variable. So this impulse is happening at tau equal to t minus t node. So the result of this integration would be a x of, and we will replace tau by t minus t node. So x of t minus t node, which is simply the input function. So the output function y of t is equal to the input function shifted at t node. So going back over here, so the output y of t will be a x of t minus t node. And here again I've chosen to keep h of tau as is and mirror and shift x of t minus tau. The same result will be obtained a x of t minus t node. And now as you can see, the amplitude, the output is an amplitude scale time shifted version of the signal x of t. So the output is the same as the input, only shifted in time with t node and multiplied by a constant a. As there is an example 2.9 textbook, try to solve it. It's an important example. Okay, so please note that convolution of an arbitrary signal, which is any signal x of t, with a time shifted impulse, simply applies the same shift to the input signal, same hold for discrete type impulses. In other words, in the previous example, we had an x of t being convolved with delta of t minus t node. An arbitrary signal being convolved with a shifted impulse will give us the same signal x of t but with the same shift x of t minus t node. So convolution of an arbitrary signal with a time shifted impulse will give us the same input signal at the output with the same time shift as the shifted impulse. More problems over here. I encourage you guys to go through the textbook and go through the solved examples in the textbook that help you a lot to understand and to practice the convolution. Okay, so the next example we have over here, we're asked to find the step response of a continuous time system in terms of its impulse response. So we are not given a specific function for the impulse response, but we need to find the step response in terms of the impulse response. So going to our whiteboard over here, we simply are saying that if we have a system, Lti system, with an impulse response h of t, we need to find an expression for the step response. So again, what is the step response? The step response is simply the output if the input is a unit step. So let x of t to be a unit step u of t, and in this case finding the output y of t would be s of t, which is the step response. So the step response is simply the output from the system if the input is a unit step. So moving on, so basically we need the step response to be the convolution of u of t with h of t. So the step response s of t is the convolution of u of t and h of t. And again, during the convolution we need to start by replacing t with tau and keeping one signal to keep it as is and the other one to mirror and shift. So let's try to do so. So it will be integration from minus infinity to positive infinity, and let me keep u of tau as is, and h of t minus tau mirrored and shifted d tau. So u of tau simply starts at 0 and goes to infinity like this. This is u of tau. So having u of tau in the integration limits will start from 0 instead of infinity. So s of t will be integration from 0 up to infinity, u of t, which is 1 right now, h of t minus tau d tau. And now let's define a new variable, tau prime, to be equal to t minus tau. And doing so, if tau is equal to 0, tau prime will be t, and if tau is equal to infinity, tau prime will be minus infinity. And now s of t will take the following form. So s of t will be equal to integration of h of tau prime. So now, first step, I have replaced t minus tau by tau prime, and of course d tau will be minus d tau prime. So we will be having d tau prime, and we will be having a negative sign over here. And next, when tau is 0, tau prime is t, so the integration will be from t. And when tau is infinity, tau prime is minus infinity, so it will be to minus infinity. And of course now this negative sign will be used to switch or flip the integration limits, so the integration from minus infinity up to t, h of tau d tau. And this is the definition of the impulse response in terms of the the definition of the step response in terms of the impulse response, integration from minus infinity up to t h of tau d tau. And in discrete time systems, we had a similar definition. S of n was a summation from minus infinity up to n h of m d h of m, summation of h of m. And of course, if the system is causal, causality means h of t starts at 0. So for causal systems, h of t is equal to 0 for t less than 0. And in this case, the integration will start from 0, not from minus infinity, because if we have a causal system, the values of h of tau will be 0 for tau less than 0. So in this case, the step response would be the integration from 0 up to t h of tau d tau. This is for the case of a causal system. So going back over here, the step response will be integration from minus infinity up to t h of tau d tau, as you have seen in the whiteboard. Step response is simply the output when the input applied is u of t. And of course, for a causal system, h of t is 0 for t less than 0, and in this case, the step response will be integration from 0 up to t h of tau d tau. And of course, if the step response is the integration of the impulse response, it means that the impulse response is a differentiation of the step response. So h of t is a d by dt s of t. Okay, another example over here. We have an LTI system whose impulse response is 1 over RC to the negative t over RC u of t. This is the RC circuit we have seen before. Let's try to find the step response of such a circuit. So we know h of t. Let's try to find the step response. So h of t is equal to 1 over RC e to the negative t over RC u of t. And in order to find the step response, simply we need to do a convolution between this h of t and u of t if you want to find the step response. So again, we can do it graphically. So if we start plotting h of tau would be like this, a decaying exponential function starting at 0. And now we need to plot the input, which is a unit step, because we are looking for, we need to find the step response. And then we will mirror x of tau to be x of minus tau, so step like this. And now we need to shift it such that this 0 will become t. And now, as we can see, if t is less than 0, the overlap will be 0 and the integration will be 0. So y of t will be equal to 0 if t is less than 0. But if t is larger than 0, in this case the overlap will be from 0 up to t, and the integration will be from 0 up to t. So we will be integrating from 0 up to t the function we have, which is 1 over rc e to the negative tau over rc d tau. And of course, in this case, since we are integrating with respect to tau, we need to divide by minus 1 over rc, which is equivalent to multiplying by minus rc. So again, y of t will take this form. Y of t will be equal to, so we have 1 over rc multiplied by minus rc. It will cancel out. We only will get a negative sign. So we will getting a negative sign, and now we will substitute with the limits. So e to the negative t over rc minus e to the power 0, which is 1. So e to the negative t over rc minus 1 times u of t. And why do we have this u of t? Because basically it's 0 for t less than 0 and have this value for t larger than 0. So the form would be, of course, this negative sign will exchange 1 and e to the negative t over rc times u of t. And this would be the step response s of t of this circuit. And going back over here, the step response will take this form, 1 minus e to the negative t over rc 4 times u of t. We have two problems in the textbook. I would like you guys to try to exercise more. As I said before, the convolution is very straightforward, it's very easy, but it's kind of confusing sometimes if you do not practice enough. You need to practice a lot in order to master the convolution sum and the convolution integral. And this will be it for this chapter. In this chapter, we have learned about the time domain representation of LTI systems. In the next chapter, the Laplace transform, we will start learning about LTI systems, but now in a different domain that's called the Laplace domain.